Hey class, how's it going? We got our last video here for power and efficiency and basically for the topic of energy this week. And so we're going to look at basically questions around power and energy. I did a little intro into it. Here we have some questions. So I'm going to do question 3 and 4 from our practice sheet. That's from the power and efficiency practice sheet. As well, I'm going to add 2 questions that I like to add in. I was going to have a whole other worksheet and I decided there was a lot of crossover. But I do want to do 2 questions from the other worksheet that I was going to give. So if you want to write these down and try them out before I do them, you can kind of do that as we go here. All right. So there's going to be question 3 and 4 from the practice sheet that already has an answer key. And I'm going to do 2 additional questions as well. So let's go through this. We have 4 questions. Hope this video is not too long. No, don't want that. Oh, sorry, pressing the wrong buttons here. All right, got the right buttons now. All right. Here's question 3. A 65 kilogram cyclist. 65, on a 50, so basically there's a mass total here of 80. All right, there's a 65 kilogram cyclist on a 15 kilogram bike. We're gonna say that they're together, they're a system, they're attached to each other. So there's 80 kilograms. Start from rest and increase to a speed of 12 meters per second in 20 seconds. So it says, what is the power output? And then we'll kind of get to this here. But let's find out what the power output was here. So again, power equals work divided by time. And a work is either a change in energy or it's a force times distance. Now I have no force and I really have no distance here. But I do have a change in energy because I have a change in kinetic energy. Started from rest, got to this speed. So let's see what the new kinetic energy is, which is going to be the change in kinetic energy. So kinetic energy equals 1/2. Mass is 80, and then 12 squared. All right, I've already got this all queued up here. And so when I do that, I have this kinetic energy as 5,760, okay, joules. So that was my change in kinetic energy, which also means it's also my work. All right, now that I have that work, I can plug it into here. I have the time already, so this isn't too bad. My power is going to equal 5,760 divided by 20. And so my power output here by this person is going to be 288 watts. So that is how much power the actual cyclist got out of this. Okay? Not how much you put in, that's how much the actual bike did its job and gave some power. For B, and I'll change colors here. Why, I don't know, but let's just because. For B, it says if the cyclist provided an average power of 400, so that means like they put in 400 watts of energy. What is the efficiency? Well, efficiency is, again, power out divided by power in. You're always going to have your smaller number basically as the top number because you're going to have a decimal, which also turns into a percentage. Okay, so how much did she technically put out? Well, the output was 288. Because that's actually what we got out of this. That's what the speed that she got out of this was that. What did she put in? She put in 400. And so efficiency equals the out divided by the in. And so what efficiency? We had 72%. Like this gives you 0.72, which turns into 72%. Okay, so remember, just whenever you get a decimal of want to turn a percentage, times it by 100. So that's actually not bad. 72% efficiency for a machine, even if it is a bike, is honestly pretty good. So not bad there. All right, hopefully that was a pretty good question. Let's keep going. All right, question 4. Oh, I don't have enough. I'm just going to get rid of question 7 there, give some more space for now. Question 7 is a question that you guys don't have yet. That's one of the new questions. Question 4, you do have. A girl pulls a 5 kilogram wagon with a force of 20 newtons, force of meters. So you can already tell here, we have a force and a distance. Force, 20, distance, 7 meters. If the final speed of the wagon was 3.5, determine the efficiency. So what this means is, like, we're looking at basically work Okay, there's no power here, but it says determine the efficiency of this process, okay? And I can find work two ways here. There's the work that she actually put in. She gave a force, and she had a distance. So technically, she put in a force here. The output is the actual like velocity. What output did this give her? What speed is her actual wagon moving at now? And so we can also find technically the outwork. So we're gonna have work in versus work out here, okay? Or work out versus work in. So let's figure out the work that she actually put in. The work she put in was she pulled 20 newtons for 7 meters. So we can do that work one with this one. That's not too bad. So basically, 20 times 7, 140 joules. She put in 140 joules. Now what actually happened to this wagon in the work sense, okay? Again, how do I find this? Well, she started from rest, we're gonna say, okay, anytime it doesn't give a VI, we're gonna assume that it started from rest. And so we have a change of kinetic energy. When we have a change of energy, we also have a work. So let's see what work actually happened to this wagon. Okay, so our change in KE, which equals 1/2, mass is 5, and 3.5 squared. And so what's our change in kinetic energy? Also our work. Our change in kinetic energy was 30.6 joules. So she put in 140 joules of energy because that's her force, that's her distance. It only got to this speed though, which means there's a lot of energy lost to friction and other things. But let's find the efficiency. Again, this is our input, here's our output. So we're going to find the actual efficiency here, which is 30.6 over 140, which gives me a decimal of 0.22 or 22%. So this is not a good efficiency. We're talking about she's putting a lot of work in and actually only get 22% of the speed out. That's not a very good efficiency, okay? So this machine, not so efficient. This wagon, not so efficient in the sense that there's probably a lot of friction between the tires and also whatever the mechanism of the wagon is itself. But this is kind of how to do this question. Anytime you have, it's looking for the efficiency of like a process, it's not always going to be power. It could just be like, what happens to our work and what work do we actually get out? Here's our process and kind of how we look at it here. Cool. All right. Let's go to two questions that you do not have on your practice sheet, but I want to go over because I've done them on provincial exams before, and I definitely do want to show them to you guys. Question 7 is not too bad. Question 8 is a little tougher, but honestly, you guys will get it no problem. So, if you want to write this down and try it on your own before I actually kind of go over it, you can pause the video, try it out. But it says a car must produce 12,000 watts, so power equals 12,000 watts of energy to keep a car moving at a constant speed. We have constant velocity of 20 meters per second. What force is being done by friction to keep us at a constant speed, basically? So, like, what kind of work is friction doing? Basically, we're worried about, like, the work done by friction. Okay, so what, so not the work. We're worried about the force. What force of friction? We want this, okay? Now, the nice thing is when you're at a constant speed, we're just worried about, again, the friction, basically. So that's going to be like our friction. We can figure out what work's done by friction first, and then we can figure this out. Now, it says here, make up a time. I didn't give you a time. Sometimes in these kind of questions, they don't give you a time at all. And why do we need a time? Well, power equals work over time. You kind of need a time. Make up a time. A lot of times they just won't give you time. I always say, it's really easy. Give a time of 1 second. Okay? Because it's a constant speed, you're going to say, what happens in 1 second? And it's really easy then to kind of figure out the rest of the question. So, if I have a constant speed, which means I have no change in velocity, like I have a lot of power going in, but I have no change in velocity, that means that there's a lot of work being done by friction. So if I use 12, like my formula, power equals work over time. If I have, my power is 12,000, and I have a time of 1 second, I can then just times by 1 becomes the same. So my work, the work done by friction is also 12,000 joules. So that's how much work friction is doing. Not the force, that's the work being done by friction. All right, now I don't have a change of energy at all, and I need to find this force. I need to find the force being done by friction. And this is where you tell Ms. Westwood, I have no distance. I understand I did not give you distance, but the nice thing is, you do have a velocity, and you do have a time. All right, and hopefully we can go back to our kinematics. And the very nice thing is that this is a constant speed. It's a very nice constant speed. So we can go back to our very, very easy or simple little distance equals time multiplied by velocity. And so if I have 1 multiplied by 20, I went 20 meters. All right. There's not too many questions where it's going to ask you to like make up a actual variable, but they do this sometimes when we talk about energy. Just always use the time of 1, and then everything else kind of fills in nicely. So here I have a distance. This car would have gone in 1 second. It would have gone 20 meters. So now that's not too bad. Work equals force times distance. 12,000 equals force times 20. Divide 20. Divide 20. And the force of friction. The force of friction is 600 newtons. Cool. So that's how we kind of look at this question here.